Hello everybody, my name is Santiago Rodriguez, software architect for the Optare Solutions Research and Development Department. Today, I am very pleased to be able to present this episode of the MEC Tech Series focusing on a real implementation of an edge application and what edge tools help us to achieve that. In this episode, we will learn how to face the challenges and limitations of developing an edge application for surveillance drones, how to use the ETSI MEC APIs to obtain the required information in a standardized way, and how to simulate a real environment with the MEC Sandbox, which allowed us to experiment with and test our solutions in a controlled way. With the focus on the 2021 ETSI MEC hackathon, we decided to implement an edge application for surveillance drones. The solution would have the following features. The drone would fly in a predefined route, also known as surveillance area. A video stream would be captured by the drone looking for intruders. Pedestrian detection would be performed by AI algorithms. Due to latency requirements and computational needs, the inference could be executed at the edge, generating flight commands used by the drone for target tracking. If the intruder leaves the surveillance area, the drone would return to the predefined route. Based on the coverage type and the power and quality of the signal, the application could dynamically modify its behavior, for example, reducing the video bitrate. It was decided that the application should dynamically modify its behavior based on the location information, for example, the coverage area, the radio network information, for example, the power and quality of the received signal, and the wireless local area network information, for example, is Wi-Fi available? The questions were, where do we obtain this information in a standardized way? How can we obtain it? The solution was the use of the ETSI MEC APIs, a set of APIs that allow us to access network and users information in multi-access edge computing environments. On the other side, the selected real-world scenario has some limitations. Drone flight involves several regulations and administrative constraints: proximity to airports, populated areas, allowed altitude, required permissions, etc. Testing with different coverage areas is not always possible due to the current deployment of 5G networks because they are not always available. A real environment test involves resources and time consumption, having no sense at the initial development phases or for learning purposes. Other limitations are the weather conditions, for example, how to deal with the drone flight on rainy days. The solution: to use the ETSI MEC Sandbox, an interactive environment that simulates a real edge deployment, working with several network simulations, 4G, 5G, Wi-Fi, stationary or moving UEs, and the most important thing, it includes the services that expose some of the ETSI MEC APIs that we need: location, application support, service management, radio network information, and WLANG access information. The first action was to create a drone in the sandbox, defining the initial location, the coordinates that it would follow during the flight, the velocity, etc. Then, the next action was the intentional selection of a predefined path for the drone to pass through different coverage areas: Wi-Fi, 4G, 5G, even areas without coverage. Further actions were related with the required data consumption. For the location information, we created a user tracking subscription which provides us with notifications about the coordinates of the drone, the access point where the drone was connected to, the previous access point, if the drone was entering or leaving a specific area, etc. For the coverage type and to retrieve the power and quality of the signal received, we created both new radio and no new radio measurement subscriptions, one per coverage type, 4G, 5G. The notifications were received in the provided callback URL. To determine if Wi-Fi coverage is available in the current position of the drone, we created WLANG access information subscription to know the associated Wi-Fi stations in the region. With all these notifications received by the application, we could know in real time the position of the drone, the coverage type of the area where the drone is passing through, the zonal status information, the current and previous access point, entering or leaving, etc., the power and quality of the received signal, and the notification received from the MEC services. This information is used by the application to dynamically adapt its behavior based, for example, on the coverage and quality of the signal. So, to wrap up and conclude this episode, here's what we've learned. How to deal with some of the limitations and constraints of edge-strong applications, such as required information or testing environments. How to use the ETSI MEC APIs to retrieve required information about location, radio network, and WLANG access information. And how to simulate a real environment with the MEC Sandbox, generating a scenario where to test and interact with the edge application. Interested to learn more? You can visit and play with the MEC Sandbox at the following link: try-mec.etsy.org. You can check out the ETSI MEC APIs descriptions, and of course, you can take a closer look at the Follow MEC application. Follow also the next episodes of the MEC Tech Series. So finally, thank you for your attention and interest in Follow MEC, the implementation. I hope you'll continue to enjoy the rest of the MEC Tech Series.